Hello and welcome back to CB2330, Scientific Computing for the Life Sciences. My name is Ian Hoffecker, and this is the third video of the first session. So in the first two videos we talked about what scientific computing is and how a program is put together. And in this video we'll talk about where our code will actually be running and how we keep it and maintain it. So we'll be using two services, two free accounts, and nothing installed on our own machines. So the two services, they're doing two different jobs. So Colab is a machine that runs our code. It's a Python machine sitting at Google, and we will be reaching it through our browser. And all this needs is a Google account. So if you have a Gmail address, that will work. And GitHub is the other service. So this is where our code will be kept along with every version of it. And there are so there'll be a record of the code and a version history, and this will all be on one page that the public can read. So both accounts are free. Neither one involves an installation on your local machine. So let's get started. If we follow the URL, it takes us to the welcome page. We create a new notebook from the file menu at the top. New notebook in Drive will create an empty notebook, whereas open notebook will allow us to access something from before. And this saves by default in our Google Drive. So open notebook has actually a GitHub tab in it, and this will also allow us to access a notebook that's posted in a GitHub repository. We can then save the notebook to our Google Drive, and we can also save a copy in GitHub down here, and this will let us place the notebook in a repository, which we'll cover in a sec. So here's an example of a notebook with one cell in it. And if I hit Shift Enter, or if I click the play button, this will run the cell. And Colab works using cells like this. So programs get evaluated on a cell by cell basis. And so here you can see that there's an output in a cell that remains printed here. And if I save the notebook, this data will be stored as well. So a notebook is a nice way to show results to others without needing them to actually run the code. And this format has a bit of history behind it. So it started with a graduate student named Fernando Perez, and he actually put out the first version. It was called IPython in 2001. So the notebook part came in the years to follow. So in 2011, and 2014, it got spun out under this name Jupyter. So Julia, Python, and R, these three languages are the languages that the Jupyter notebook was first supporting. And then in 2017, people who built it got the ACM Software System Award, and this is a prize that has previously gone to things like Unix or Internet protocols or the World Wide Web. And so this thing we're going to use, this is kind of a 25-year project. So let's have a look at what's happening just to understand here. So with this setup, you have the browser open. You're not running Python on your computer. So instead, you're using the browser to access the machine that Google service is running somewhere. And on that machine is a Linux installation with a recent version of Python and a handful of packages installed. And so Google doesn't tell us which machine we're on or where it is, but we don't have to take their word for it. We can actually ask the machine. So if we run curl ipinfo.io in a cell, the server reports back its own address and the city that it's located in. So for a free runtime, this usually comes back somewhere in the United States, but Europe and Asia also can turn up, and you don't get to pick, actually. And it's worth running once because, for the first time in this course, we could answer a question about the system by measuring it rather than actually looking it up. And so we can see here, if we run a few system queries, we see what version of Python, the Linux installation, some hardware status. And so this means we don't need to install anything locally. And regardless of whether you're on a Mac or a Windows or a tablet or whatever, you can still use this service as long as you have an internet connection and a browser. So the catch is that your server time is limited. So if you allow 90 minutes to elapse and you're idle, or if you spend 12 hours in total, the runtime will disconnect. And you can, of course, just connect again, but you'll have lost whatever objects have been stored in the server's memory. But the notebook is kept in your Google Drive, and so anytime you want to run the notebook, you can just connect to Google Server again and access Python. And the data you generate, the code you write, this will still be kept here on your drive. So next, if we run like this pip install line with the exclamation mark here, this will actually send this bash command to their Linux server and install a Python package that might not already exist on their server. So we have these ways to interact with the machine itself, not just the Python interface here. And we'll sometimes use commands like this when the default settings may lack something that we need. So if we return to the system query cell that we showed in the last slide, there's a line here that we can explain. So import and the names of some Python modules or packages. So import loads a module, and this is a file or a piece of code that someone else wrote and tested, and it gives us all the functions from that file under this import name. So import sys will give us the sys module, and then sys.version reaches into it. So the dot means it should look inside the module for the function that we're calling. And Python has natively something like 200 default modules. This is the standard library that ships with Python itself. And outside that, there's the Python package index, or PyPI. And anyone can publish. So this is sitting around 900,000 projects as of now. And so Python starts nearly empty, but we can ask for pieces that we want. And that's why it's good to spend a minute on these import statements. So Colab also adds NumPy, SciPy, Pandas, and Matplotlib on top of the standard library. And these are modules that are quite useful for scientific computing, so we'll be using those in this course. And none of these are loaded until we run this import statement. So here we've renamed NumPy to NP. This is just a convention, so you can do this for packages that have long names, for example. And you'll typically see, for example, matplotlib.pyplot get renamed to PLT. So this is just a convention or a habit. But it's so widely used that maybe it would look strange to see anything else. So for this course, I'm going to encourage everyone to try these exercises without AI assistance. And if you go to notebook settings, you actually have an option there to hide generative AI features, which appear by default. And again, the reason for this is that we're going to use this class time to train our brains, and you're assessed in this course for participation in these sessions only, not whether your code works. So there's not that much to be gained by getting the answers instantly with AI. You have to sit here anyway, and if you're stuck by the end of the session still, and maybe you're facing a situation where, okay, I'm not going to finish the exercise, or it's not going to get done, then you could you could use AI if you're really irretrievably stuck, let's say, and you could turn on this feature, and you could also ask questions that maybe didn't get answered during the exercise. So you're welcome to use AI help to understand things better, but I would try to delay this moment as long as possible and allow yourself to struggle. And if we imagine we're in a sort of gym for our brains, AI is the equivalent of using a forklift to pick up these weights for us. There's not much point behind it. And there's evidence behind this, so this is not just my feeling. So there's a study from Wharton School from last year, published in PNAS, so about 1,000 high school students working through math problems. And one group got GPT-4 chat, an interface and a kind of tutor version with guardrails that wouldn't hand over the answer, and the other got nothing. And during practice, the plain chat group looked good, and they solved more problems than the control group. And then when the AI was taken away for the exam, that same group scored 17% worse than the students who never had it at all. So the practice session had been, augmented by the AIs, and so the tutored group came out level with the control, which is interesting. And so it's not the model that's kind of doing the damage here. It's getting the answer without struggle. And there's another study from MIT on essay writing. So that's kind of pointing in the same direction with a smaller group, like 50 people. So this is just a couple studies, but it kind of matches what we would expect. And we see that it doesn't really serve our purpose to be lifting weights with help, because the weights are there for us, if that makes sense. And we're not doing the world any favors by writing basic functions for well-established scientific computing principles, which we're here to learn, but which are already known by the world and already established. So these exercises exist just for our own mental training. So turn this thing off at the beginning of each session, I would suggest, and allow yourself to get stuck. You won't be penalized for it, and the lessons will stick better when you do manage to get yourself unstuck. So moving on, in this next slide, let's discuss version management. So when you're writing code or a project, especially a large one, you will often get something like this happening, where you have different versions accumulating. Why? Because you're being careful. So you make some major change and you want to reserve the possibility to revert back to a backup state of the program that was working before you started on this new feature or major restructuring job. And this can get quite messy. So maybe these files end up in different places. You have one on Google Drive, another on a local machine hard drive, one in an email that you sent to someone. And if you're writing code for a scientific manuscript, maybe at some point you need to find out which version we had to use to make this figure. And this is data that we're publishing, we're reporting. So now it's our responsibility to have a good understanding of our own pipeline and code base. So if you no longer have that version anywhere, now you're in trouble. So we want some kind of version management system that lets us keep track of the history of our code base, and we'll use something that's called Git. And Git comes out of kind of fight. So this is a good way to remember it. So the Linux kernel team had been using a proprietary system called BitKeeper for free. And in 2005, this arrangement collapsed over a kind of licensing dispute. So Linus Torvalds, who had written Linux, he stopped and he wrote his own alternative instead. And he started this in 2005 with the first commit that was submitted on April 7th. And by that first commit, Git was already kind of tracking itself. And so this what it does is it stores the complete state of a folder at a particular moment that we choose, and along with a message that we leave each time where we make a note about what the state was doing. And with this system, we can go back and we can look at these moments again and retrieve everything from that particular state. So Git is this versioning system, if we go to the next page, and actually it's something that can run locally on any machine. And these moments, we refer to them as commits in Git terminology, and the folder that we're talking about is what's called a repository. And so most people are familiar with Git through an online service called GitHub, and this is what we're going to use in this course. GitHub showed up in 2008, so a few years after Git, and what it added was not the version control, so this part was already established. What it added was this social layer, so the page, the profile, and the ability to look at other people's histories. And then in 2018, Microsoft bought this for like $7.5 billion, and there's something like almost 200 million accounts on it now. So if you don't already have a GitHub account, go ahead and make one. It's free. You can go to github.com and sign up, And before you do anything, I would recommend going into the Profile and Settings menu and just review what is and is not public there. So you can decide, for example, if you want your email address to be kept private or displayed. And when someone clicks your profile, they'll see a kind of portfolio of your public projects and whatever information, the bio, website, etc., that you want to display. So do this before you do anything else, because every commit records an author email address, and this travels with the repository forever. So a public repository will put it out in front of internet scrapers. So if you don't want your email to be public, then watch out for this. On the other hand, having your email posted can enable people interested in your work to potentially contact you, so employers or collaborators, etc. So on the next page, we have a new repository. So if we create a repository, we can give it a name. So let's call it CB2330 portfolio. And I suggest for simplicity to make one for this course. So call it whatever you like. And we're assessing participation again for these sessions. So you'll provide me with a link to your repository, and we'll simply check that you uploaded something for that exercise. And you can add a description and decide if it's going to be a public repository. By default, a free account requires public repositories. And you can add the README now. So if you switch this on, this is not just cosmetic. So what it will do is it will force us to create the first branch in the project, or the first lineage of the repository's contents. So switching this on will create a README file and submit the first commit, and then the repository is then working. So and then skip the git ignore and the license for now. We may come back to this later. On the next page, so a commit is version snapshot. So git's unit is the commit, let's say, and a commit is one of these snapshots of your state of the code. So here we can imagine a piece of the lineage of a repository, some analysis program, let's say, and each of these boxes represents a snapshot of the code at some moment in time. And it holds every file as it stood at that moment, the name and mail address of whoever made it, the time, and some message. And each commit points back to the one before it. And so that chain of pointers is the history. Now, because each commit holds the full state rather than the difference, any of them can be reproduced exactly. So we can go back. And because each one points at its predecessor, the order is unambiguous, even when you have several people working or making commits. And the message is what carries some important meaning. So the commit that just says, update, it doesn't record anything except for the timestamp. And if you write something more detailed, like fixed the off by one error on the data .csv file, this makes the history searchable, let's say 6 months down the line when you're trying to figure out what was going on. And so we're writing it for this kind of future person who's reading it later. Usually it's us having forgotten what we were doing at this time. And so nothing has been sent anywhere yet, let's say. And everything on this page is kind of happening in the folder on a machine. And so send it to GitHub is referred to as the push. So one first commits, and this happens locally usually, and then one sends the commit to the cloud. So on the next page here, we're looking at taking another look at the pipeline. So Git has these three phases. So on the left, the files we're editing, analysis.py, notes.txt, some output image, and editing a file changes it there and not anywhere else. And then git add marks a file for the next snapshot. So that's this arrow, and notice that only analysis.py moved in this case. So you decide. And notes.txt and the PNG file stayed where they were. So git commit takes the snapshot and puts it in the history on the right permanently. And the reason for this middle step is that we usually edit more than we want to record. You know, for example, image data, maybe this is temporary, or we have some files that perhaps are not important for the code base, but which got generated when we were working with the code. So a day's work might involve one real change plus some minor debugging, and staging lets us choose what the real what changes go into the history. So this involves these commands, and this in the case of the add step, we're not producing an output, so this doesn't print anything. But then the files that were edited and not added, would not make it into the commit. So we have to pay attention to this. So then the last step is git push. This is the third step, and it's doing something different from the other two. So it's sending the commits to another copy of the repository, and this one is living on GitHub because in our case the Colab runtime is getting thrown away, and the version on Google Drive is typically going to represent only the latest version of the file. To be fair, this is not quite the whole story. So Colab actually does keep a history of its own file, like a revision history, and so Drive keeps revisions underneath that. But Drive tends to prune them roughly every 30 days or sooner. For example, if several versions have piled up, so unless you go in and mark one, noted for keeping it for permanent records, you're going to lose this. So this is kind of a safety net more than a record. And Git is really the system that lets you intentionally keep a history on purpose. So that's the arrangement, and the rest of the video will kind of talk about how to set things up. So for our purposes, we'll just go to File and save a copy in GitHub, and this will accomplish these three commands that we described earlier. So the command will run these operations: add, commit, and push. And the first time we use it, we'll be asked to do like a GitHub sign-in and authorization for Colab. So you then select the repository, you select the branch, the file path, and you write a commit message. So it's best practice to write something thoughtful there, and you can enable an option to include a link to Colab. So then if you access the notebook from GitHub, you'll get a little badge that gets added at the top that lets you open a fresh runtime in Colab with that notebook. So next, if we go to the list of commits, we see that every message that we wrote is there, and the history of the repository and each branch. And so here we get every snapshot in the repository with the newest first. And if we click one, GitHub will show what changes happened. So that's this diff. So the red are things that were removed, green are things that were added line by line, and we have a backward pointer drawn as a link that we can follow. And the messages are what makes this list usable, so this is why it's important to write them. And one thing I should mention is that the system has some limitations when it comes to Python notebooks. So our file format that we'll be using, this IPYNB, IPython notebook file, this is actually a JSON file with the outputs and the execution data stored inside it. So anytime you rerun a notebook without editing a line, this will still register like a large change, and so this diff view will fill up with this JSON data. And GitHub will render the notebook nicely, but this diff will not look like much if you're committing notebooks after running them. You can turn the outputs off if you want to. So under Edit Notebook Settings, there's a box that says Omit Code Cell Output when saving this notebook. So if you tick that, Colab strips the outputs out of the file and stops saving them from then on. And then the diffs go back to being readable. But the cost of this is that the notebook in your GitHub is then only code, so nobody sees your figures unless they run it themselves. So for this course, I would leave the outputs in, and you'll just have some ugly diffs. But the notebooks, people will be able to see the plots and kind of results that you generate. So next, a repository after some time will have multiple files in it. And so here we have 2 files, each showing the message from the last commit that affected their contents. And the README is rendered below. And by the end of this course, you'll have, let's say, like a list of each session exercise, and this list will work a bit like a table of contents. And so each time you commit and push from Colab, your files will end up here. But if you want to add something else to the repository, so for example, maybe you want to add a .py, like a pure Python file, not a notebook, you can do that here with add file and create new file. You type a path, type the contents, etc., and commit. And again, this involves writing like a commit message. So it's the same model from the last few pages, and it's typically like a 25 megabyte cap through the browser, and 100 megabytes if you're pushing from a command line. Yeah, even if you have like the paid subscription, that doesn't remove these caps. It's the same limit on every account tier, whether it's free or not. But the cap is not really the problem. So even with this lifted, a repository is not a place where you should keep large data files. So we won't keep raw data there, for example. Instead, we'll keep code that fetches this data from somewhere else. So next, so we've been using this term branch a couple times now, referring to this like lineage of the repository. And we have a drop-down menu on the left here that lets us create a branch. And we typically have the main branch, it's called. And in the drop-down, we can decide to create an experimental branch where we say try to introduce a log access to our code. And maybe we think this is a bit risky, so we want to do this without potentially harming the main code. So we click it, the branch is made. The drop-down now lets us switch between them, and the page that follows has all the files, the README, the commits in that branch. And the branch also shows up in the Colab's save dialog, so you can work on a branch there. And then deleting a branch actually doesn't eliminate anything other than the name. So commits it pointed at are still in the repository. The main consideration with branches is that merging 2 versions of a notebook means merging this JSON file. So a branch where the same cells got edited on both sides creates a number of JSON-related conflicts, and it's typically good not to keep a branch unmerged with the main for too long, because it starts to diverge. So every commit that goes into the main is a commit that the branch doesn't receive. And so if you're working in a project with other people who are, plugging away at the main, your branch will get left behind at some point. So best practice is to have only one branch at a time. You merge it quickly. And for our purposes in this course, you won't really have to worry about any of this. Just save to the main each time. This is how we're going to work. But I'm talking about branches here simply because it's a major feature of this system, and it's good to get some exposure to this idea early on. So next we have the README file. So so for any file, if you'll have this pencil icon, and you can open the file for editing in the browser, and you can commit changes. You have a button on the top right, so you don't need to actually install anything. You can add, you can commit, you can push, you can do this all in the browser. So we can try this with the README file. We can open up an editing window. We can add some text to explain what our repository is for, how it's structured, add a little table, and this is using Markdown. So this is the same format actually that text cells in a Colab notebook will use. So when you're not writing Python code, maybe you're writing some text. So this uses Markdown format. And there are a few little conventions, like if you want to create a heading, you use this pound sign or the hashtag symbol. And so do this for your repository for the course, make a little table, describe what the repository is about, and what's the format, how can an outsider run the contents, do they need to install something, give some instructions. Okay, so now for the last page. So here I just want to show how my research group is using GitHub. So we think of it as a kind of portfolio showcasing some of our projects and work. And you can do the same for your personal page. So I think it's nice to start thinking about starting to cultivate your own personal identity through the projects that you do and what you create. And so the assignments in this course, they're not graded for accuracy or anything, just participation, right? But it's in your interest, let's say, to organize yourself well and present things nicely and put your best effort forth since it's on display. And so under one's personal settings, you have a jobs profile tick box one can select to indicate that you're looking for work. And GitHub can be a place that recruiters might look to find competent engineers or scientists. I'm not sure how often this actually happens, but there are figures circulating, so something like 87% of tech recruiters and so on. Yeah, I'm not going to quote this exactly because I'm not entirely sure about this, but the point is that there are something like 180 million accounts on this platform, and GitHub sells a hiring product basically to companies, and they built an open to work setting into the profiles. So that tells you something about who they think is reading. And for us, the groups page might be a place to look if they're deciding to collaborate, if someone is looking for to apply for a position. So none of this is required for this course. This is just an argument for making your CB2330 portfolio public if you so choose. Make it a showcase for your creativity, your ingenuity, your technical skill, your responsible coding practices and conscientiousness. Yeah, that's all for this video. So as soon as you have the system set up and running, we'll be ready to dive in and start exploring scientific computing concepts. So see you next time.